Welcome back, folks. And now we move to something which is probably much more interesting than the representations. So far, all the correlation clustering algorithms that we had were tailored at detecting linear arbitrary oriented subspaces. Now, one question is, what happens if the objects within a given data set are of nonlinear nature? If they're like located on a parabola, or if they're located on sine or cosine functions, how can we capture that? And well, one approach that we tried with the Huff transform, again, is to see if we can use the Huff transform to detect also nonlinear correlated clusters. And one endeavor that we made in this direction to go beyond linearity was to span a axis parallel parabolic Huff space, or hyperparaboloid, if you would say, for higher dimensions. So the question that we have, since we had like alpha 1, alpha 2, up to alpha d minus 1 and delta as the axis in the linear Huff transform, the question that emerges is which features or which dimensions would the Huff space consist of in the quadratic case? Well, as you see here, like these two parabolas that we have, one here and one here, they differ in two aspects. First, they have a different vertex. So this xp, yp, and xp and yp, these are the vertices of these two parabolas, 2 and 2, as you see here. And here, as you see, it's like 5 and 3. And they differ in the opening. So this one, the green one, is more open than the blue one that we have. So we have like two parameters. We have like one, the vertex, which can consist of several dimensions, like of the x dimension, the y dimension, the z, or x0, x1, x2, x3, xd, the dimensions that the original data space has. And we have this additional dimensionality of the opening. And the opening is like the horizontal distance from the focus of a parabola, if you recall from high school, to the closest point of reaching it. So you take the focus and draw a horizontal, or in the other case, a vertical distance, and try to reach the closest point, or the point that you can get here horizontally. And you recognize, okay, then this here is like the opening P. And this one is like the directrix that we have put, yeah. So the characterization here in this quadratic or hyperparaboloid parabola is in 3D a paraboloid, and a paraboloid more than 3 dimensions is a hyperparaboloid. It can be characterized as follows. So in this case of 2 dimensions in data space with the vertex of 2 and 4, we have like here xp. This is like the direction of the vertex for the x dimension of the vertex. This one here is for the y dimension of the vertex. And this here is like for different openings. And what we did here, again, you see each object here, each of these points becomes one object function. So you see how they must be also one with like 6 and 8, for instance. So this green colored line, or at least what can be seen in this mess, is like the object function for this particular object. And how does the function look like? Well, it's xi minus vi. So you take the object x, the first coordinate, like 6, minus its vertex minus 2 squared, divided by 4 times the x0. Okay, sorry. So you take here, in this case, the y coordinate 8 minus the 4 minus the vertex, the second coordinate. So 8 minus 4 is 4. Then you divide it by 4 times the first coordinate here, like you see 6 minus the first coordinate of the vertex 2. So this is 6 minus 2 would be 4. 4 times 4 is 16. And we had 4 divided by 16. So you have here 1/4 as the opening P. And here, long story short, it happened the same stuff like in the linear Huff space case. You try to scan for areas where most of the functions intersect, and that this area is as compact as possible. And this is actually the black point that you see here. So this is where most of these object functions do intersect. However, you recognize you do not have here this sinusoidal functions as you had in the linear case, but now you have like two parabolas, one here and one here. So one with the opening upwards and one with the opening downwards. And here in between, so where these two parabolas seem to meet, this is like a point of singularity, or actually an area of singularity. Why that? Well, what happens if both of them would be the same? So if this x0 would be 2 and v0 would be 2, this part would get 0, and we have an area or a point which is undefined. So this is the reason why you have like two parabolas, one here and one here, two paraboloids to be precise. So, well, this is, however, one approach how you can capture or scan for paraboloid correlations, or axis parallel to be more specific. We haven't in this paper investigated arbitrary oriented parabolas. This is one way that you can detect a non-linear correlated cluster. So these objects are not correlated linearly, but quadratically. So quadratic function is characterized through vertex in the opening of a parabola. The drawback is it's limited to hyperparaboloids of revolution. This term revolution means it's axis aligned. It does not cover hyperbolic paraboloids. Hyperbolic in the sense like if you go in higher dimensions, let me sketch it actually for you. We should go here. Pen. So if you say, for instance, x equals y squared, to have like a simple example, then you can go in higher dimensions and say, for instance, z equals, sorry, that was garbage. It's actually y. I blame the heat because it's quite warm here. So if you go through 3 dimensions, you probably have then x squared plus y squared. Plus y squared. And now you may ask, hold on, we've got here a plus sign. What about a minus? Can't we also add here x squared minus y squared? And this is exactly what happens. If you have a positive sign, like x squared plus y squared, then you get like this in 3 dimensions. It's not a parabola, but it's a paraboloid. So it looks like a bowl or something. And if you have a minus sign, then it is like a Pringles chip. So the thing starts to look like different. In polynomials of higher degrees, like degree 2, degree 3, and so on and so forth, you have like more type of variance of your function. And this gets especially even worse if you have like 4 dimensions, or not worse, but more complex. If you've got 4, then you have like plus and minus, because you have x squared plus y squared plus z squared equals w. And then you have like plus minus, you have like plus plus, you've got like minus minus, and so on and so forth. So you have like much more different combinations to go for. And it gets more difficult in higher degree polynomials. So this is one insight that you get, that you have much more different variants to cover. And alternative forms are possible, like Hessian normal form representations. So that what we proposed here is, again, not the only way of how to represent a parabola. You know, probably from high school, like, what is it? Ax squared plus bx plus c. This is how you can also characterize. And then a, b, and c from ax squared plus bx plus c, a, b, c, are then in this case also something like a normal vector, so to speak, which we know from the Hessian normal form. Well, then let's go from quadratic functions to a different nonlinear type, and these are periodic functions. And now you may ask, how the heck are we going to represent? Well, half transform or parameter space transform, it's already in the name of parameter space. So always, if you wish to model or design a nonlinear half space, ask yourself, what are the parameters of that particular function that you wish to detect? And in case of a periodic function, you have the amplitude A times sine of the period B times x, so here you have y and x, minus the horizontal shift C plus the vertical shift. So you can have the amplitude, so like higher or lower. You can have like the periodicity or frequency modulated. So how frequent is it? You have the horizontal shift, so is it more left or right, so to speak, and you have the vertical shift, so is the whole periodic function more upwards or more downwards. Ask me in the tutorial to illustrate that for you, because there are nice tools or computer-aided tools for showing how it changes if you modify the different parameters here, that you get an impression of that. And so this is like for different amplitude, this is for different periodicity that you have, this is for the horizontal shift, and this is for the vertical shift, just that you get some impression of that. And it can be represented through these parameters, 4 parameters, phase shift and frequency, phase shift alias horizontal shift, and frequency alias the periodicity. However, so this was already it about the periodic function. Here you see the half space, so you see all those sinusoidal waves that are represented through this function. It gets quite messy and complicated, and this is only for like x and y. If you introduce like higher dimensional like x, y, z, if you have more properties or features, it will go skyrocket. And having now the example of the polynomial degree 2, so the quadratic and the periodic functions, well, questions that emerge is like name use cases in which it may be interesting to detect actually such nonlinear correlated clusters. Well, in a quadratic case, scenarios where domain experts think that part of the data may have evolved from some quadratic system, like the expansion of volume with increasing temperature is quadratic, or in periodic case, detecting within a given data set different periodical patterns like seasonal patterns or seasonal correlations between versus global annual correlations. However, and this is the take-home message, it is difficult to justify nonlinearity in correlation clustering. It's like similar to kernels. The same question is like, which kernel to use? Do I use a polynomial kernel? Do I use a Gaussian kernel, a spline kernel, and so on and so forth? And why am I going to use that? So it is up to the domain expert or to a user to choose which kernel and why. And this makes things actually difficult. Now you may say, okay, what should we do? Well, what you can do, the correlation clustering, the linear one itself, is also a way or a mean to detect nonlinearities. Because if you recall, local PCA itself has been used to detect in 1993 in the NeurIPS paper to detect nonlinearities within a data set. The only difference is that you do not provide a more complex nonlinear function like a periodic function or some polynomial function, but you say, I don't care how complex this function looked like. I don't even want to know that complex function. Just piecewise linearly approximate, PLA, piecewise linear approximation, approximate the actual data. So you may get a lot of approximations, but that depends on the granularity, how precise, how good do you want to have that approximation. As mentioned, a parabola, you can approximate through, for instance, 2 lines, one here and one here. You can say you want to have 3 lines, one here, one for the vertex and one here, or you can have like 5 lines, 6 lines, as many lines as you wish. So you can go arbitrary, precise, arbitrary, precisely approximate that particular nonlinear function, not knowing anything about if it's quadratic or whatsoever. So what I suggest in case of doubt, or what is actually also a good way, use correlation clustering, use like local PCA to achieve a piecewise linear approximation, regardless how complicated it is. Here, those papers that we published in that case for quadratic and periodic, they are nice to investigate and to see how it is possible, and that you can, in theory, also like approximate or detect any specific nonlinear function through half space, but not more. So it's more like a theoretic interest or academic interest. So far on that, and stay tuned for the next part. So thank you.